Alright, hello everybody. We're going to discuss section 10.6, which involves reaction mechanisms. So let's talk about what a reaction mechanism is. Well, it's basically a series of steps. And so at the beginning of the chemical kinetics chapter, we talked about how wanting to know the steps is important because we can understand the reaction more, and that will help us take advantage of those steps in some sort of manufacturing process or just for chemistry knowledge. So we want to learn more about the steps of a reaction. So let's take a look at this example. So we have nitrogen dioxide gas plus carbon monoxide gas goes to nitrogen monoxide and CO2. Well, this reaction and lots of reactions can be much more complicated than how they appear. We can use the balanced chemical equation to determine amounts using stoichiometry and things like that. But there's a lot more going on than what we just see in an overall balanced equation. So if we look at the rate law for this reaction from experiment, we have determined that it's equal to K times the concentration of NO2 to the second power. So this is a second order reaction. Okay, well, like we said, things are a lot more complicated. And so when we actually look at this overall reaction in more detail, we see that its mechanism, or its series of steps, is composed of two steps. We've got nitrogen dioxide gas plus another goes to NO3 gas plus nitrogen monoxide. And the rate for this reaction can be said to be K1. So this is step 1. Here's step 2. Okay, and the rate constant for this reaction is known as K sub 2. So we've got two different reactions with two different rate constants. Well, an intermediate is the species that is neither a reactant or a product. It's formed and consumed. And if you look at NO3, NO3 is formed in step 1, and it is used up as a reactant in step 2. So it's needed for the overall reaction, but it is not part of the overall reaction. So it's considered an intermediate. Each of these steps is considered what's called an elementary step. It's a reaction whose rate law can be written from its molecularity. And well, molecularity is the number of species that must collide to produce the reaction indicated by that step. So we're going to look at what type of things are colliding together as reactants in order to produce products. Okay, so let's look at molecularity a little bit closer. There are three main types. Okay, first type is unimolecular. Well, uni implies one. And so here we've got one thing colliding to produce products. And so because we can determine rate from molecularity, our rate is just K times the concentration of A, or A to the first power. So unimolecular, rate, order of 1. Okay, we've got two types of bimolecular. So bi meaning two. First, we've got two of the same species combining together. So we have 2A producing products. So our rate is equal to rate constant times the concentration of A to the second power. So because we have two of them, this is second order. The other situation we can have is where we have two different species colliding. Okay, it's still bimolecular. And since we can determine the rate based on the molecularity, our rate is rate constant times the concentration of A times the concentration of B. So this is a second order overall, considering that they're each to the first power. Okay, let's look at the third type, which is termolecular. Termolecular is rare. It's hard to combine three things together. And so we've got A plus B, or 2A plus B, forming products. And so the rate law for that is equal to K, A to the second power times B. So third order overall. Termolecular, meaning 3, third order. So they do go together. The other situation we can have with termolecular is three different species added together. So A plus B plus C gives us a termolecular molecularity. And our rate law is concentration of A times the concentration of B times the concentration of C. So again, that gives us third order overall. So this is what they mean when we say we can determine the rate law based on the molecularity. They are kind of equal or the same.
Okay, this is unimolecular molecularity. So you have one species and it'll kind of not spontaneously combust, but this is like something that might be radioactive, so boom, products. Okay, so if we look at bimolecularity, you have two different species, could be one of your options, or two of the same species. Unfortunately, I do not have two of the same Hello Kitty Pez dispensers, so we are only going to show one of the types of bimolecular. So we've got two different species, they collide and react to produce products. Okay, termolecular, we have three different species that are all going to collide in order to produce products. So they are far apart, slowly getting closer, 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 collide, and produce products.
Okay, so now that we have talked a little bit more about what reaction mechanism is, let's look at a more specific definition. A reaction mechanism is a series of elementary steps that have to satisfy two rules or two requirements. The first one is that the sum of the elementary steps must give the overall balanced equation. So when we put all those elementary steps together, we've got to get the overall. The second rule is that the mechanism must agree with the experimentally determined rate law. So we said we could determine the rate law based on molecularity. Well, that has to agree with the experimentally determined rate law. So let's look at our example from before. Here is our overall reaction. This is what all of our steps need to equal to. So let's look at step 1 and step 2 together. Now we want to cancel out things that are the same on both sides. So here's our intermediate as the product and the reactant. Okay, here's one of our NO2s as a reactant. Here's one of our NO2s as a product. If we write everything else down that's left, we have NO2 plus carbon monoxide producing nitrogen monoxide and carbon dioxide gas. And if we compare this with our overall, they are the same. Okay, and that's what we want. The second part is to look at whether the rate law matches the experimentally determined one. Well, in order to do that, we have to determine what's called the rate determining step. It's the step that basically controls the rate. It's the slowest step of all the steps put together. So if we assume for this one that our rate determining step is step 1, which would be this one right here, then that means that the production of CO2 is controlled by the formation of NO3 because it is formed in step 1 and then used in step 2. And so if step 1 is really slow, formation of NO3 is going to be really slow, which means then it won't show up as a reactant very quickly, which means CO2 won't be produced very quickly. So that's why step 1 is our slowest, and it's based on NO3. So we can write the rate law based on the molecularity. So let's look at step 1. For our reactants, we have species A plus another of species A producing products. And so if we've got A plus A producing products, that means that our rate is equal to K times A to the second power. Well, our A in this case is NO2. Okay, so since our rate of formation of NO3 is the rate of NO3 divided by change in time, we said it was equal to K1, because remember that's step 1, times our NO2 to the second power. Well, that's exactly what we just talked about here. So that gives us an overall rate of K sub 1 times the concentration of NO2 to the second power. And so if you remember from previous, this was the experimentally determined rate law. And so they are equal. And so that's good. Well, a mechanism can never be proven absolutely. Okay, we say that it's close. So if it satisfies both requirements, we say that it's possibly correct, but there are always there's other options. We can't ever say it's absolute. All we can do is first determine the rate law, then use chemical intuition and make sure that those two rules are satisfied. But other mechanisms may exist, and so you have to experiment. Okay, so this pretty much finishes up 12.6. If you're bored, here is some homework to get started on before class, but otherwise we'll go over some examples and then discuss it. Have a good day.